So actually I'm starting the session. Okay. भाई कहाँ पे है? बोल रहा हूँ स्टार्ट करने देना हाँ। हाँ मैं स्टार्ट करता हूँ फिर मेरे बाद स्टार्ट करना ठीक है. So hello, good morning to all of you. So I think I'm audible to everyone. Please comment in chat box whether I'm audible or not. Yes, okay, thank you. So let me start with myself. So I am Dr. Pratyush Kumar. I recently completed my Ph.D. from IIT Bombay, and with the help of some IIT alumni, we have started this company that is IteraSim, and this company is committed to the providing the innovative simulation solution to the industry and academies. And this means we have started conducting some works on the CFD machine learning, specifically focusing on the open form ANSYS and Abacus kind of softwares. So we have already conducted some of the workshops, and currently there is a weekly workshop is going on related to open form programming specifically. So we conduct weekly workshop on the open form programming, and currently we are in the last phase of this workshop session. And this webinar session we have started from the means this is our first webinar, and in future we are also going to conduct some of the webinars related to CFD, CFD-ML. Okay. Now about the today's sessions. So today we are going to cover about the EV simulation essential with the ANSYS. So where we are going to means explain about the comprehensive training on the EV simulation using the ANSYS software. And today's session is designed for both for the beginners and the intermediate users, where we will cover essential topics such as the basic navigation, tool utilization, and advanced model techniques for the simulation electric vehicle systems. And by the end of sessions you will be equipped with the design and analyzing the AV components effectively. And so this session is going to just give you idea that how you can perform EV simulation using the ANSYS. So of course this is a broad topic, so we will not able to cover the complete means essential related to the EV simulation. So this session is going to just give you a brief. Okay. Now, before starting the sessions, let me give you some idea about the speaker. So this speaker is Dr. Akshay Kumar, and he is also completed PhD in the fluid and thermal engineering from the mechanical department of the IIT Bombay. And he has experience with working is the open form as well as the ANSYS software. And currently he's working in a good company of the electric vehicle simulation company. Due to the confidential, I'm not going to put the name of that company in this session, but he is expert in AV simulation and advanced modeling of the component related to the AV simulations. So with extensive experience in the academia and industry, so he will guide you through the practical advanced techniques, helping you to apply these skills in the real world AV simulation project. So with these introductions, and let me just give you some means some instruction that please don't turn on your mic during the simulation during the session. After the completion of the session you will get a chance to ask your questions. So please don't turn on your mic during the session. After that we will give you chance, and if you have any questions just try to use the chat box, it will be better. And with this I would like to hand the mic to the Akshay, and Akshay you can start your session. So thank you to all of you. Okay. Yeah, yes Akshay, you are audible. Yes, Akshay, you're audible and you can start your session. Yes, it is visual.
The challenges engineers face and better and more reliable. We have divided this webinar into two parts. First, we discuss the basic understanding of the EV thermal management. After that, we will try to simulate some EV traction motor. We will tell you how can we simulate, how can we design different components, and in this basically we will focus in the hand in in terms of hands-on experience. We will focus on the EV CFD simulation of the fan designing as well as the electric motor thermal simulation. First, we discuss if we talk about the EV powertrain. Actually, if we compare it with the IC engine, it replaces the traditional internal combustion with electrical components that work together to drive the car. If we talk about IC engine, there are some components like cylinder piston and the exhaust system, nozzle, fuel tank system, and the crankshaft. But in case of that EV powertrain, basically there are three systems, mostly as electrical motors that convert electrical energy into mechanical motion. Another is the battery pack that store the electrical energy needed to power the motor. Another last one is the power electronic that manage the flow of energy between the battery and the motor. And another accessories are onboard charger to charge the battery, and the ECU electronic control unit that converts the supply from that manipulate the supply from battery to the motor so that we can get the power and motion at the will of the driver, at the will of the requirement of acceleration and the velocity. And next is the architecture of EV traction motor. This is mid type of motor in which you see there is a shaft, and another way is the rotor in which magnet are placed to generate the electromagnetic effect. After that, there is a stator in which the winding is there, and in the left side you will see that copper winding, and the white material it is insulating material. It prevent the current leakage from the winding to the that stator of the system. Here you see the end term, open term of the winding, that is called end winding. End winding is not connected to the any part of the system already, that connecting to the that stator by the that insulating material, white material, that is varnish and maybe another material. It is non electrical conductive, and its thermal conductivity is also relatively lower. So if you can see that end winding doesn't have any conduction heat transfer, in that it is conducting the heat using some insulating material. So it is necessary to conduct the heat from winding to the to dissipate the heat from the winding, otherwise it will fail, or it will fail, or otherwise it will degrade with the time drastically. So first, if we talk about that low power rating motor like by e-bike motor या rickshaw motor, in which we generally cool the motor using the fan and using the natural convection from the casing of the motor. But if we talk about that higher power rating motor, that is used in the that SUV cars and sedan car, which have the capacity of around 120 to 130 kilowatt, in which it is very necessary, it is mandatory to dissipate the heat from the end winding. Otherwise it would fail after some time, or otherwise its performance will be degraded. According, if we talk about that electrical point of view, the motor perform well up to the winding temperature of 150 degrees centigrade. But as the temperature goes beyond 150 centigrade, its performance degrade with very drastically. In terms, if we talk about that most maximum efficiency of any electrical motor, EV motor, that can be 90%. Mostly it operate in terms of 85 to 90%. But when the temperature of winding goes beyond the 150 degree centigrade, it performance with 5 degree centigrade increment, its performance goes down to 50% or 60%, or otherwise it will fail after some time, some burnout will take place. So it is mandatory to manage the heat of e-powertrain. Another one, what is the application of e-powertrain? E-powertrain are used in variety of electrical vehicle. It replaces the combustion of internal combustion engine with electrical components.
Akshay, can you
E-powertrain,
zoom your screen? It will be better. Can you full screen your presentation?
yeah, it is full screen already.
Uh,
1 minute. Now it's
yes,
okay.
yeah, it's okay.
Okay, okay. E-powertrain are used in a variety of electrical and hybrid vehicles. These applications are growing as we move towards more sustainable transport options. Here are some common applications. First is low power EV motors, that is used in electrical scooter, bicycle, and small three wheelers and e-bikes. Another is Another segment is 20 to 100 kilowatt, that is compact size electrical cars. If you talk about, if you see in like Alto cars, and such as the Nissan Leaf or Hyundai Kona EV, and hybrid electrical vehicle to save the fuel. So few companies shifted to hybrid mode of power generation. First they can provide the power with the gasoline or petrol, and they can use the electrical power developed by the electrical motors. Another, the high power EV motor, that segment to 100 to 200 kilowatt, mostly sedan and high performance car are operate in this region, in which like Tesla Model 3 or Audi e-tron. And in this, if we talk about EV thermal management, if there is a car of 150 kilowatt, and we say that its motor efficiency is 90%. So if how much, if it 100 kilowatt into 10 by 100, so how much it will produce 10 kilowatt heat continuously. If we need to dissipate this heat by using some coolant and liquid and some air, so that there are in that high power segment, basically uh, dissipate the heat using the air and fan, it is impossible task. So mostly in this range we mostly use that liquid cooling, and you can say some another mode or some hybrid mode of cooling system, like natural convection liquid cooling, as well the passive thermal energy storage system, like we can use phase change material for in localized heating zone, and we can use also heat pipe in some electronic circuit. And there another segment is ultra high power motor, that is above 200 kilowatt, that is mostly very high powered car, and mostly the trucks and as well as the buses in that. And why thermal management is critical in electrical vehicles? Actually electrical vehicles nowadays, if we talk about, they have been come to the market on the road, but still there are a lot of research is going on in terms of performance, in terms of battery, and in terms of power generation. So there are actually, if we talk about that thermal management, the mostly the global player in this domain, like Tesla and other player, they are still changing their cooling system. They are still changing their cooling system to make the more efficient machine. In terms of that, if we talk about Tesla, earlier for that high power segment, it was using spray cooling for cooling the end winding. But nowadays they have been shifted to another thing. They are using gravity and some suction created by the RPM of the motor to make the machine more efficient. So there are still research are going on in this field. And here actually why it is necessary, first is prevent the overheating. The battery, motor and electronic control system generate the heat continuously, which cause damage if not properly managed. Another thing, improve efficiency. Keeping component at the right temperature ensure that they work at their best and waste less energy. And another will extend the lifespan or extend the life cycle of the system of the machine. Proper cooling prevents wear and tear, helping the battery and motor most longer. Another last one is the enhanced safety. Mostly managing heat reduces the risk of fire and safety hazard. Otherwise, some you can see that some cars or some EV can pick the fire if there is not proper thermal management, or thermal management fails at any time. So it may be fired and it may be blast after some time. So it is mandatory to design the most efficient thermal management in that electrical vehicle. And if we talk about what are the losses in electrical vehicle, first and major loss that cover that 80% or loss is the copper loss. Copper loss means refer the power loss due to the resistance of copper winding in electrical components. And if you talk about, I think you must be aware that electromagnetic effect, because motor works on electromagnetic effects. So in motor there are two losses, one is the copper losses, another is the iron losses. And if you talk about that rotor in which the magnet are fixed, that that used to generate that magnetic field and electric field combination. So we talk about copper losses, the power generation of that heat generation in the copper of the winding equal to I square I RT, where resistance is the function of the temperature. As the temperature will rise of the winding, the resistance will rise. So it actually, if we need to optimize that temperature, we need to control that temperature. Another one, the iron losses. The losses occur in rotor as well as the magnet. First is the First is the eddy current losses. Eddy current, why it is caused? It is caused by circulating current induced in the conductive core due to the changing magnetic fields. And these currents flows in the loop within the core, generating heat. To reduce eddy current, core materials are often laminated, breaking up the paths of these currents. If we talk about that eddy currents, it is although the function of the temperature, that is resistivity, that is the function of temperature. Another one is hysteresis losses that occurs due to the repeated magnetization and demagnetization of the core material as the magnetic field changes. Every time the magnetic domains in the core align with the field, energy is lost in the form of heat. If you talk about the formula of heat generation in that core system, that is hysteresis losses. That is the, if you talk about, that is the function of the temperature. If you talk about the mechanical losses, that that is mechanical losses, they are very minimal, that are friction losses in bearing, so we can ignore it. But mostly we have to cover that losses in electronics, losses in that winding, and losses in the rotor system, that is the magnet. Another thing is the cooling strategies. As we discussed, that there are different type of cooling system: air cooling, liquid cooling, heat transfer, enhancement, integration cooling. If we talk about air cooling, that is the natural convection using the outside air, and some forced air cooling system using that fan, or we can also use nozzle for generating for
to avoid any localized heat generation, in which we can use air impingement cooling. And if we talk about liquid cooling, that is very popular in that high power segment, and in terms of cooling of data center and cooling of higher configured electronic system, that is jacket cooling. Jacket cooling means that is non-contact type of cooling. It is generally used in that electronic circuit, because we can't expose the electronic circuit to any liquid, otherwise it will be fail. Another is a jet impingement cooling. In any localized, very localized heat generation, a localized heat source or any point, we can use this technique. And that is spray cooling. That is very famous in that one high power segment zone, and companies are using it extensively in high power zone. To because what why they are using, because that utilize fine droplets of the liquid sprayed into the surface to enhance heat definition. First is the uniform cooling. Another, when we cool the using the fine droplet, the surface area of the cooling will increase. And what is the mechanism? Because as the fine droplet evaporate, they absorb significant amount of heat from the surface, lowering its temperature. And we can also get the advantage of that latent heat of the evaporation. So in very lesser area, we can remove the more heat. Another one is cooling is a uniform cooling. It will be sprayed into the uniform area of the winding. It will cover every part of the winding. And another one, that it use the latent heat part, because after evaporation of liquid to the vapor, so it can dissipate more heat instead of other applications. And another is that it increase the surface area. The small size of the droplet increases the surface area for heat transfer, enhance the cooling efficiency. And if we talk about the spray cooling, it is everywhere used in cooling electronic component where high heat flux are generated. Very high heat flux generated means higher heat is generated in leisure area. That is why higher heat flux that is named as. And in this, actually we can use also cooling electronic component, but we have to use some dielectric oil. Actually the oil should be that electrical non-conductive. If we talk about water is a electrical conductive, so in this zone we have to use that, or some dielectric oil to use it in the spirit, use in the that electronics cooling system. And another one is the one of the advantage of that, it is space saving. Actually companies or everyone world is going to develop the compact system, high performance system in lesser space. So in this, that is the advantage of spray cooling, that it is a space saving cooling, require less physical space compared to the design a bulk cooling system like chillers or large heat exchanger. So it's, if we want to develop a compact system, electrical or electronics compact system, that is a high performance system and generating the heat continuously at a very high fluxes. So for that, it will work as a space saving, and it can dissipate, it can absorb more heat in lesser space, and it can be easily added to various applications and skills. That is also one benefit. Another one is the immersion cooling. In immersion cooling, mostly in EVs nowadays, it is not used very extensively, but in data centers, they are using this immersion cooling system very at very large scale. And this is a cooling system where electronic component or the entire system are submerged in a thermally conductive liquid, a specially formulated dielectric fluid in that use. And that is make a direct heat transfer, in which there is no agent for heat transfer, no wall or no anything. It is a direct heat transfer. The liquid absorb heat from the component directly, promoting efficient thermal management. And in with the mechanism is that conjugate heat transfer, conduction and convection. Conduction in parts electronics or any material part, and convection in that liquid. And where is the application? It is mostly use that data center cooling, increasing used to cool servers and equipment, improving energy efficiency and space utilization. And if we talk about in cooling that you can say winding cooling of that electric, it doesn't use in that segment. It mostly uses in battery thermal management, because in nowadays battery thermal management is also necessary with that electrical motor. Otherwise battery can be thermal run out, or it can be fail, or it can be blast, or it can catch the fire. And it also use that power electronics. So if we talk about the application of immersion cooling in that EV segment, that is used for battery and power electronics. And nowadays people are using, if we talk about that quantum computing, nowadays people are using it for that quantum computing cooling, that is CPU and GPU system. And it's one of the advantage that it is direct type of cooling. No other another in that there is no power consumption to drive any pump, to drive any fan. So it's a static type of system, and it is highly efficient. And it also it also save the space of the system. And in which it first of the one of the most advantage of that, it eliminates the noise generated by the fans and air circulation system. If we use any pump or fan, so it will generate some noise. But in immersion cooling there is no noise generation, because it is static cooling system. There is no moving and rotating equipment in that. But some challenges are the initial setup can be expensive due to the need of specialized equipment and fluid maintenance also needed time to time. Okay, to prevent the contamination and degradation. And another thing, the compatibility selection of proper material is crucial to avoid reaction with with the cooling fluids. And another is the high that heat transfer enhancement, that is used with these air cooling system and liquid cooling system. These works as a enhancement. These works as to perform the to make the to improve the performance of thermal management system, in which mostly they use thermal paste, heat pipes, and phase change material. And if we talk about people are companies are using integration cooling system, in which they are using that heat transfer enhancement, liquid cooling, air cooling. So they are combining all three to get the to develop a high performance system. And what is the challenges in e-powertrain thermal management? What so mostly there are some challenges that is written over that heat generation in multi components. And one in that the scale of heat generation is different for every part. If you talk about winding, it would generate the heat at very higher rate. If we talk about electronic system, it will generate the heat at slower rate, but you can say the heat generator of generation of heat flux would be higher, because in a less space it would generate the higher heat. And one of the there would be many system integration and air cooling, liquid cooling. But for actually if we talk about an automotive system, it works on different scale. You need to optimize it, you need to optimize in terms of cost as in terms of performance, because it's a very competitive market. If your system in you develop a system in which it is taking that 100 rupees extra as compared to the previous system. So if we talk about they are going to they are going to sell around 3 lakh units of any car or any EV unit. So if you multiply, so it would affect more. If you want to develop any defense system or any you can say unique system for your lab, for one time usage, so it's okay, there is no extent if you increase the cost 500 or 600. But in terms of automotive market, you have to optimize the cost as well as the energy efficiency. One is the compact design and space limitation, that is also the issue. And cooling during fast charging, means while charging the electrical vehicles battery, so mostly they use the fast charging time in which heat generation is higher. Sometime battery get blast during the charging. So for that, during the fast charging, we need to develop such a management thermal management that it can remove the heat from the that generation heat generated from the battery and charger. And some that the thermal system also degrade with time, so we need to consider that. And in that, one of the critical thing is cost versus performance trade off. That is very essential in that one, in which advanced cooling system improve battery lifespan and efficiency. That is one thing. If we talk about that performance system, and trade off, these system increases overall vehicle cost due to complex design, material, and integration. And instead of, if we talk about that, air cooling system are more affordable and simpler to implement. So limited trade-off means limited cooling efficiency can lead to reduced battery performance and faster degradation. So one thing, if you are using high performance system using liquid cooling, so it would be costly. And if we using but it would increase the efficiency of the system, means increase the life of the battery, life of the that EV motor, but it would be costly. But in term, if we talk about low cost system, means air cooling and the cooling using passive system like heat pipe and phase change material, they are affordable and there is a one type of cost, but their efficiency will be lesser as compared to the liquid cooling. So if we need to optimize this, striking a we need to strike a balance between the cost and performance is crucial for EV manufacturers. Innovations such as hybrid cooling system and optimized material choice help mitigate trade-offs between that cost and the performance. And that we have also discussed that compact design and space limitation. And one thing is thermal runaway in battery, that is also mandatory to discuss. It is that, what is that phenomena? It is that self accelerating process where the battery's internal temperature rises uncontrollably due to exothermic reaction, leading to the failure that can cause fire as well or explosion. And that is because overcharging or over discharging mean leads to internal short circuit failure. External damage may be the issue, but chance of external damage is very lesser. Internal short circuit, it may be happen because of the that product design. And high temperature exposure accelerates the breakdown, means if the battery is exposing to very high temperature environment, means the components like motors and electronics are generating the heat at very high scale. So this may also cause to the failure of the battery. And if we talk about how can we that overcome these challenges, first we what we want to increase, what we want to decrease. First we want to increase the efficiency, power, thermal management, and reliability. Another, what we want to reduce, on another hand, we want to reduce total loss, weight, volume, and cost. So sometimes we have to optimize. Nowadays they are, because mostly company they are using some machine learning modeling, some data, some statistical model, so that they can take a decision in terms of cost and the performance of the system. And what are the trends in thermal management? That what the nowadays they are developing integrated thermal management system. They are doing that, we will add that passive cooling, air cooling, or natural convection. We will use the liquid cooling also, and we will use that in thermal enhancement technique also, that we will use heat pipes to avoid the heat generation in any localized heat zone. Or we will use that phase change material because it can store the heat. So their company are using this type of system, and they are using for fast charging also, because nowadays they are developing that the charger in such a way that they can charge the battery in few hours and few minutes. So nowadays, to thermal management of fast charging, it is very mandatory in such a cases. And enhanced motor cooling techniques also, in which they want to cool the motor at the optimum temperature, and some solid state thermal management means they want to increase the surface area of the heat dissipation. And one of the AI and predictive control, predictive modeling, that is also the one way to optimize the thing, to make the decision makers work easy. So in that they use the advanced algorithm and machine learning models that predict thermal behavior based on real temperature data. So mostly they put the thermal sensor, some load condition, some driving pattern basis on the previous data, and basis on that temperature data and load condition. So they develop a system in RTO. If there is any localized heat zone, so they will provide some coolant, they will provide some heat and the part of the motor, and how can we simulate it. And one of the fan design that actually for to develop a proper thermal manager, we should know how can we design a efficient fan, we can design a efficient heat sinks, how can we efficiently design a heat exchanger, how can we design a spray cooling system. So if we break down the problem into small segment, so we should know about the every component, every mechanism, every cooling system. So for that, separately, every CFD engineer who want to work in that EV thermal management, he should have some idea about the efficient design of each component of the system. So first, in this range, first we discuss that fan design of the mostly the fan, that fan of for the EV design on the basis of Euler turbo machinery equation and cascade theory. And what Euler turbo machinery it provides the relationship between the change in angular momentum and energy transfer in turbo machinery. So it is a key to predict the fan performance. Mostly the what is the use of that system in that one, you you want to find the blade angle mostly if we're using the that turbo machine equation. If we talk about that is the velocity triangle for a that for a axial fan. In axial fan you take whether u equal to the peripheral velocity of the fan, and if you do a u1 and u2 is equal in that axial flow system, axial fan, and it will w1 is the relative velocity and cf is the flow component of the velocity, and u equal the peripheral velocity. And if we talk about the outlet triangle, and in which first if we want to design a system, first we need to calculate the blade angle, that is gamma 1 and gamma 2. And mostly blade are designed from leading edge to trailing edge, mostly from left to right system. So using that turbo machine the equation I have written in short, but if you will go through, yeah, we will go through in detail. So we will find various things like to avoid the circulation, what we can use recirculation, and to develop a higher performed fan. So how can we develop a higher performed fan? And in that, if you talk about the meridional velocity, that is the flow velocity, you cannot, that depend on the value that flow rate require upon RT means is the tip diameter of the fan, and RH here is the that hub diameter of the fan, and where is the n is the revolution per second of the that fan. So actually basis on that flow rate we require, we develop that blade angle at the inlet, you can say. And basic or what is the pressure development by the fan. In fan there are two things basically. One is the that pressure development by the fan, that may be static pressure and total pressure. Another in the what the that fan will, how much flow rate that fan will generate. So using that turbo machine equation we can found the we can put the pressure, and we can found the cut is the that flow velocity component, horizontal component of the flow velocity, and basis on that we can find out the that flow machine generate to get Yeah, is my screen visible to you? Hello, Pratyush.
Yes, it is visible, but
Workbench is visible.
workbench is visible. But can you zoom it little bit?
Okay, okay, one minute.
And also you can hide this stop sharing this at the yeah.
Okay.
Yes, it's perfect.
Yeah, yeah. I discuss it with the start. First, there is if you talk about that terminal of the blade, there would be a blade gen tool. Yeah, that is ANSYS blade gen tool. Yeah, you open that.
Where you are working, please zoom it little bit. Akshay, I would
Hmm.
suggest please go slowly and also zoom it. The work, the means the portion where you are working, please zoom it out.
Okay, okay, one minute.
And go little bit slow.
Okay. Yeah. Yeah, that is actually if we want to in that blade gen tool, we can develop different type of fan. Actually, if we talk about turbo machinery, we can develop any part of the turbo machinery like turbine, fan, compressor. So first we will discuss that normal axial fan, in which firstly if in terms of that to develop of the fan for ev parts, ev thermal management, so mostly that blade mostly depend on the angle and thickness. If, and second one, the pressure and suction. If you are going to develop any impeller or any device that would have a higher suction, like a engine cooling engine intake fan of the any engine, or you can say aeroplane or everything. So you can develop it using that pressure and suction. So in our domain, we will discuss that angle and thickness model. So I generate a small fan. Small fan means which has that I am generating at origin to which had that length of 18 mm and that 12.5 mm is that let's say we change that, let's say shaft diameter of the fan is 15 mm. Okay, so basically you if shaft diameter of the 15 mm, so 7.5 mm will be the radius, but at the that near the shaft we want to increase the thickness of the hub of the fan, so that we consider 12 mm of the that hub radius from both the side at inlet and that trailing edge and at the leading edge. Okay.
So can you, so Akshay, can you again repeat that half diameter? Means we did not get it. Akshay, can you repeat this thing that diameter and half thing you have explained?
Direction of the fan, and in that actually we are designing a small fan so that we can mesh easily. So in which the fan length is 28 mm and fan hub radius is 12 mm and fan tip radius at the leading edge is 40 mm and trailing edge is 80 mm, and you can get these value depend on the requirement. Actually, if you have a space constraint that you want to develop a fan which should have the dimension like that, axial length should be that one, and the that height of the fan should be that one. So basis on that you have to fix, and what performance you want means in terms of flow rate or in terms of pressure development. So you can change in that one, that in equation and the angle finding, and basis on that angle you can put these angle over there and you can design the fan. And here if you talk about angle thickness, after that you can give the angle. Let's say I am giving a variation of angle from leading edge to trailing edge 45 degree, and at leading edge I am taking the 2 mm radius. You can also basis on the that thickness of the material depend on the that blade fan blade material. Mostly if the blade material is have lesser stiffness or lesser strength, so you have to design a thicker fan so that it can be structurally stable. But if the you are developing a fan of metal, so you need not to consider more thickness, because it will increase cost, because it will develop a thicker fan. But we don't need of that. Also, if we increase the thickness of the fan, to the drag or friction on the fan will be increased. So sometime on increasing the thickness after some time, so it will degrade the fan performance. That is also so we also discuss, we also need to consider the that fan blade thickness carefully. And here I told you that cascade system that divide the leading edge to trailing edge in 10 small layer. So mostly I consider that 10 mm layer, and mostly we will develop that 8 number of blades for the fan. You can also increase the number of blades depend on the requirement. So that is leading edge, that is the trailing edge, and that is the angle, and that is the thickness. You can also change the thickness of the fan from leading edge to trailing edge according to your requirement. And also the angle according, if you want to find that at my that blade angle at my leading edge is 20 and outer edge is 40 25, so you can do that. So you can adjust accordingly. Another one, that is the inlet domain, that is the outlet, and that is the fan that fan body. So in that, if that is horizontally, let's say we want to put that 50, yeah, minus, we want to generate a small fan. So let's say we put it minus 15. We don't want a bigger inlet. And mostly it is the best practice to develop the fan on the origin of the system. It will because it will easy to manage the dimension. And here also horizontal dimension is 15 mm. I am not changing vertical, that is hub, that is the height of the fan. I'm just changing the horizontal direction. Okay, that is the way. After that we can also give the blades here. And second one, if you want to any cutoff means you want to contain any gap in hub and shroud. Okay, so here leading edge and trailing edge, we can say that gap in hub means the lower portion on which the fan is mounted. So basically on that best practice 0.05% gap we want actually. So mostly in good practice you can take 5% gap, 5% gap of overall system dimension or overall fan dimension. And if you talk about shroud, if you give 5% on the shroud also, and 95% the total fan body in the requirement dimension. Oh, sorry. 0.9. Okay, and now first one, there are few options here. First is we come to the model. So model where you talk about that you are generating a blade, and you need to talk about that component type. It should be fan. First you can develop different according to the requirement. It will change the configuration everything. So first axial, negative means the suction side would rotation type. Negative means negative here, that anti-clockwise. from the rear axis of the jet, from the inlet portion of the jet. And positive means clockwise. And model mostly we are generating in mm, so we can put the mm over here, and we can check how our fan will be looking like with the blade. And here I some we gave the that fan blade angle abruptly, so it is giving some deformation. So according to we can adjust.
So Akshay, can you explain what is this beta and theta angle from the diagram?
beta Beta and theta diagram, that angle in degree, that is the angle variation from leading edge to the trailing edge. And that another is the normal layer thickness of the blade from leading edge to the trailing edge. Now you can see that that is the one blade we can generate using that. After that we have generated one blade. In that you need not to develop the entire fan if you have generated one blade. And that green one represent the hub part, and the that net portion in that one, tip at the tip, it provides that surround part of the fan. After that we will close it. Mostly in meshing, mostly people use the turbo meshing, but in that you can use the design modeler also. first jump First you check the geometry, take a mesh part, update the that one blade in that geometry. It will take some time.
So after this means blade creation, you are using the mesh mesh modeler.
After that blade generation, we need to consider that one.
That is
Means that one to design the entire fan, because basically use in that design model we can generate a blade. After that we have to that patternize the every blade. Let's see, we are developing a fan with 8 blades. So based on in design modeler or any design software, we will do that setting we can develop any fan over there. Yeah, I show you one thing. That is the geometry. Here you can see that first is the tool, another in first what we do. Yeah, I show you from starting, otherwise it will be difficult to. First we take a plate. Yeah, I zoom out. Now it's visible.
yes, it is visible.
Okay, okay. After that we will take that mesh part, and we will give that update that geometry with the blade.
So for eight means eight blades you are taking. So how much elements would be there if you are doing a meshing?
Actually in that turbo machinery we require some fine meshing. So if we go in that workbench meshing, so it would be around 55 lakh component, depend on the size of the fan. Yeah, now you have that is inlet portion, that one. and that is outlet portion, and that is outlet portion, and that is fan body. Fan body means that is a combination of two. that that one, if you talk about, that is a solid portion of the board, the material portion, and another is the fluid domain. Outside the blade there it that blade can automatically generate a fluid domain or air domain outside that blade. So mostly we are doing that CFD simulation or fluent simulation, we need not to consider that solid portion of the blade, because if we go for structural way, so we have to check whether that blade is structurally stable or not. But in this case actually we need not to consider, otherwise it will increase the unnecessary mesh count. So in that we suppress that solid portion and we will take only that fluid portion. So what is that fluid portion? This is all yellow portion is the air, and that one, that profile of the blade, it will work as a wall, it will work as a cavity. So that for that we can reduce the mesh number of mesh count if we don't consider that meshing in the solid part, because we don't want anything inside the material from CFD point of view. We want to capture we want to capture only that work done by that wall, by that solid cavity and by that wall. So we will in that domain we will suppress that solid part, we will consider only fluid part. After that it is only a one blade. After that what we will do, we will pattern over here. Pattern means first which type of pattern we want, because fan are circular, so mostly we will go for circular pattern. And geometry we can take only one geometry, that is a axis, normal axis. So we will take plane normal axis because it will generate at the normal side of the plane. And another is how many copies were, because we have one copy, so we will take seven copies of that one, so that we can generate the fan with the eight blade. Here you can say there would be eight blade. Now they are separate part of the blade. So first we need to, because we want to develop a single fan, we need not to consider every fan blade separately. So first we will do, here is a technique of combine, that would be boolean. So what we will do, we will select all blades and we will unite them. So it will generate a blade fan. Another thing here are, it is giving one portion, now it's a one body. But if you go for CFD simulation of that blade, so first we will rotate only the fan part, inlet part and outlet part need not to be rotated. So first we need to separate the body into three segments. One is inlet part, one is fan domain, another is the outlet part. So in that we will actually first we will create a plane, new plane, and actually we will change it by
Sir,
plane.
please go slowly. Please, you are going very fast.
Okay. 12 foot. Okay. Yeah. Actually, in that one, we want to separate the three different bodies to that fan. First is the inlet, second is the fan, third is the outlet. So in that first we separate three into different body. So we can do it by plane, slice by plane. So first we will consider a plane. So first, because here the length of the blade is 14 mm here, so first we will separate by that one, by plane. So first we will take fan one axis, and that will be minus 14 mm, because fan length is 14 mm. Okay. Another one we want to separate at the that here at the leading edge of the part. So we will create another plane, and that will be from plane xy only, because it's origin, so it is easy to take the dimension, because it's a 40 offset by z axis, because z is the axial axis in which we will take 14 mm. So here you can generate a plane over here. Now you need to slice by plane. Create slice means to separate the bodies from by plane, by any point, by any edges. So I am considering it by plane. So here first I will take plane 5 and I will slice. It will divide it into two parts. One is the inlet part, another is the another part. Now we need to separate by plane 6 also, so that we can get the separate outlet domain. So here we can get a plane 6, or here you need to go select it on all bodies so that it can different generate different bodies. So here you can see one body, second body, and here is the third body, that is the fan. So you can name selection here, name here, that is fan, that you can give as a name as a fan, and here that is inlet domain, and that is outlet domain. That we can do. Here we have separate three domain. Okay, after that we have developed a fan which have separate domain. After that we will minimize it and go in the mesh part.
So Akshay, I have a question that we have given the thickness to the inlet and outlet domain.
Hmm.
So means
Thick-
how much this thickness should be there while we are doing simulation? Is there any criteria for that?
No, actually it doesn't have much effect mostly on system, but actually that dimension of if you want to install this fan like in any radiator system or in any car you want to sit out, there would be a particle space where you want to install the fan. So basis on our what the space available to us, so we need to give that inlet domain and outer, and mostly these machines are compact, so we minimize that inlet domain outer, so only we put that way that it can develop a that suction zone and pressure zone. So
Okay.
that, so mostly it depend on the that requirement of the system. But if you talk about that you want to develop for any aerospace application, so you have to think about it, you have to develop as a bigger, because here where in that part suction is very higher and pressure development side is very higher, so you need to consider in that way. But in terms of that fan machinery and everything, you need not to worry about that dimension, you can take according to the space requirement. And here one thing, first that contact region it automatically generated, so it is better, otherwise it will create some difficulty in meshing. So first I delete that, create that contact region. Okay, after that we will mesh basically. So first we will take that CFD meshing, and that one fluent, that will automatically come. And mostly for turbo machinery you can take that maximum size of the that element 4.5. Okay, mostly 4.5 maximum size we can take. And in sizing basically we need to capture capture curvature proximity, yeah, we need to curvature of the proximity, yes. And actually here, actually we can actually in that fan system, if the fan speed is very high, so we need to provide that inflation region to capture the boundary layer near that one blades. If we talk about that one blade, okay, so here is that blade. So if we want to capture the boundary layer effect, if you want to simulate that fan accurately, so you have to give that one inflation layer to capture the boundary layer near the trailing edge and near the that solid portion of the blade, or yeah, wall of the blade. But if you want to you don't want that, you want to find a rough approximation at how much flow rate that fan can generate. So you need not to worry about it. You can give that automatic that one inflation after that, and in which if we go none, so it will generate that tetrahedral as well as a hexahedral method. It will generate a combined type of meshing, and in that statics it will give you that one. So it will take time, so I will show you that one, how the meshing how many number of mesh element can be there in that one. So first I show you that meshing and setup, otherwise it will take our 30 minutes in meshing only. First I will check you meshing.
Akshay, I have questions. Suppose this method that you are using for the fan
Hmm.
blade design. So this same approach can be applied to the design of the turbine blades or other means applications.
Yeah, you can apply this portion, but in that model properties you have to select that turbine, and different type of turbines are there, so you have to select accordingly, and basis on that analytical modeling of the turbine, you have to calculate the angle on the basis of theory of turbine. So component to component theories are different, and the angles finding angle calculations are different. So basis on that you can calculate, but the modeling procedure would be the same.
Means this meshing and setup would be the same.
Yeah, meshing setup would be the same, but in turbine actually they are very their rpm is very high as compared to that one fan. So mostly in that one actually we need to provide that inflation layer, boundary layer near the blade and near the solid part. So we need to calculate that one boundary layer radius carefully on the basis of theory of boundary layer and basis of the turbulent model you are using. So in if you are using SST K omega model, in that, so K omega have some theory to find the first boundary layer based on that. So you can wall function and everything. They are basis on that you can find the first layer, and you can give a growth rate after that. After there is two way, one way that how many layer you want and what should be the thickness of because near the solid body the layer would be finer, it would have minimal gap. But as we go beyond that one, from the solid part or rotating part, the it would course it have a course because it's a growth rate. If we say that uh, at the near to the that solid body, the boundary layer radius is inflation layer radius is 1 mm, thickness in 1 mm. If you want to increase the growth rate of 1.5, so or the second layer inflation layer thickness would be 1.5 mm, same it will increase. So but near the that solid part it would be a final layer, and there are various calculation based on the turbulent model you are using. You can calculate the that first boundary layer thickness, yeah, first inflation layer thickness. Yeah, also in solver if you want to roughly expect, you can give a that maximum thickness of the boundary layer, and you can give a growth rate. On the basis of growth rate it will calculate the first layer radius automatically. So that is also the way. Yeah, that is the meshing. Here, automatically we give inflation to near the solid part. It it generates some fine meshing to capture the proximity at the leading edge and trailing edge, and also there is a tetrahedral type of meshing. And in the first, what you need to come in CFD point of view, first you need to check that quality of the mesh in mesh metric part. Actually, first from CFD one, basically I first check that skewness. Mostly if skewness is beyond the zero point 0.9, so your result would not be accurate, or otherwise so that setup would be fail after few simulation. So first you need to check the skewness of the mesh in that one, and it should be below that 0.9. Yeah, 0.9 maximum, it should be below than 1. Skewness means how much the mesh deviate from its you can say real body. If you are using that tetrahedral mesh, means how much it is distortion of the mesh is occurring. That calculate on that is the calculation of that one skewness. So here it would show you the skewness because mesh count is high. So here you can see that mesh count, it is 0.85. It is not, it is below the 0.9, and maximum you say the number of element that are that 0.5 range, 0.38 range, and that is that so this is okay. But if your skewness goes beyond that 0.9, so you would not get accurate result, or set fluent will not give you the good result, otherwise it would fail after some time. And we actually use that automatic inflation. And if you check about statics of that one, in which there are, so it is 6 crore elements are there in that meshing. We gave that some fine meshing to capture the more accurate, but otherwise you can give 11 or 10 maximum that element size. So it can be lower. But if you want to capture more accuracy, so you have to give some finer type of meshing. And in this, after that meshing, we I know you how to set up that case. And mostly I take that it depends on your machine computation power. So basically 30 to 45 you can take the core processors. And in that meshing I want to discuss one thing also, that you have three body. First, show all body, because it is hidden. Show body, and part two, show body. Okay, that one. And in that one, first is the inlet. I also provide a bend support over there. So here you check that inlet is the that portion, air inlet, that from that end fan would suck the air. And outlet here I gave a smaller outlet because I want to flow the air at the casing of the motor. So I gave a support structure here, so that I don't want to any flow in that domain, because I want to, because if you check about the motor, so there is a air casing there at the periphery of the motor, there are fins. So I want to flow that air on that periphery. That's why I provide a solid support over there, so that I can give the flow of the air to that casing part only. And one, because I have deleted the that one uh, contact zone, so first I need to connect the three bodies. So if we were talk about inlet domain, hide all other body. So here use that is inlet body and interface one. Interface means you are connect the body using the here in mesh you have to give the name as interface, so that in fluent or setup you can connect these different body, so that it can provide the continuous flow. If you would not connect these bodies using the interface, so there is a, you can say there would be no continuity of the flow, so it would fluent would not start. So if you don't want contact region, so you have to give interface. so that you can connect it in that one. Otherwise you can form a part also, to three component you can develop a part. I want here different part. My purpose of get develop different part, so that I want to that frame rotation or rotation of the fan to only fan. I don't want to rotate inlet and outlet in that one, so that I as that I broke that whole fan body into different part, and interface 2 and 3 the fan inlet part and outlet part. Interface 4 is the part of the that one outlet part that I gave the name of interference. And don't confuse with the interface and interference. Interference is different and interface is different. Here we go to the setup. Because mesh count is high, so it will take some time. Meanwhile I close the meshing because it will use some core of the that PC. So it, to increase the speed I will close it, and I will close also design modeler. Pratyush, hello,
Yes, yes,
what is the
yes.
time limit?
You can continue. Still, there is 30 minutes left.
Okay.
Okay.
I after that I will show that e-rickshaw motor simulation. And
Yes, yes.
yeah,
Also, it means apart from this blade and other things, you can also show that what are the different modules available in the ANSYS related to the e-vehicles.
okay. E-vehicle mostly actually in terms of e-vehicle, in terms of thermal management part, there are two model only, because there are ANSYS Maxwell. It is for designing the EV motor. So that is from electrical point of view. If you design a motor means from electrical point of view means winding and magnet. If there are that number of winding, how much would be the electromagnetic generation or EMF generation? So that is from electrical point of view. If you talk about thermal point of view, so mostly for simulation there are two part. One is the ANSYS Fluent, another with the ANSYS iSpec. ANSYS Fluent you can do the that simulation of non-electronics part, but in for if you want to go for simulation of electronics part, so it is better to use that ANSYS iSpec, because in which there are some inbuilt model. You can give that sync directly without design. You can provide the sync dimension and it will generate a sync. Same fan and same everything means if you want to give different ICs, or you can say electronic MOSFET circuit and chips, so you can directly generate. So that is better. So there is only two parts in that one.
Yeah, you can show on the after opening the ANSYS modeler. After
Yeah,
completing this session,
yeah. I will show. Yeah.
also I have one question, Akshay. So,
Hmm.
as you mentioned in your slides that you can use AI and ML kind of the predictive system to optimize the component design.
Yes.
So, is ANSYS also support some kind of the AI and ML modeling
Yeah,
system?
and since it started that on, if you have heard that gradient descent for
Yeah, yeah, gradient
optimal.
descent.
Actually in that if you simulate something, if you want to that minimize some term means you are minimize the friction losses in any
Yes.
fan or any design. So after simulation you can use that gradient descent terminology is there also, and I have also explored that one. I have to.
Yes.
So in that you can minimize the, if you give that I want to minimize the friction, so it would you give that ANSYS would give you the automatic the dimension of that component. in order to minimize that dimension. But you can't trust more in that ANSYS and whatever the that mechanism it is using for optimizers. It is better you get the simulation result, you get the that one uh, say that analytical modeling result, or you get the result from some testing data. Then you apply your own model. So it would be better because you would have more idea.
Yes,
Otherwise, in ANSYS, you have to trust blindly whether it is doing or not doing. And even for big systems also, Pratyush, it is very difficult to run again and again because
yes,
mesh count is in crores. If
yes,
we are simulating that high
exactly.
voltage motor, so it would be a 500 component, many components to simulate the entire body using the server also. So it require more time. So
Yes,
if you have the data, so you can develop a prediction model, regression or any model,
yes,
and based on the regression model, you need not to run again. If you want to find that parameter should have this value, so automatically based on data, it will give you the final dimension, that dimension it should have to give that
yes.
desired result. So from my point of view, it is better. If you have any better idea, you can also share.
So you said that there is only gradient descent. So that is only one kind of the ML model. So
That is for maximize or minimize something. But I think it would be more term, but I did not explore.
okay, okay,
I
got it.
mostly use that in that Python coding in that one to develop my own model based on my data.
Yes, yes.
Yeah.
So what is means just one comment. What is the difference between like ML model and also you said that you can use your own analytical model?
Analytical model means analytical model based on the physics of fluid flow and heat transfer. Fluid means if you are developing a heat exchanger, so there are some heat exchanger theories in which NTU and that overall heat transfer coefficient at that dimension and that one. So there would be many. So basis on that theory, first when you develop any product, okay,
Mm-hmm.
first you develop any product that you company or any client would give you that I want that flow rate,
Mm-hmm.
that pressure in that space, okay,
Mm-hmm.
and your fans should have consumed that much power. That is the constant. On
Okay.
basis on that constant, you design you develop a rough calculation, means so that you can get the idea, so
Mm-hmm.
that you apply the physics and theory of that fluid flow and heat transfer and of that component. Then you would have such some rough dimension. After that dimension, you will design your fan and you will simulate it, and you will simulate, so you will have surety whether, because that is 1D calculation analytical.
Mm-hmm.
They that would never give you the accurate result. That would give you the results below and higher 30 and 20%. Okay.
Mm-hmm.
After that, in CFD simulation, you simulate it and you get the confidence whether it is developing or not. After that, again you will change the dimension, again you will simulate after
Yes,
that.
yes.
Yeah. But if you have proper data, if after simulation you can modify your analytical calculation, basis of analytical calculation and simulation, so you would have 100 data points, some data points you would have. After that, you can impose a machine learning model, and after validation of machine learning model, you can also, you need not to run again. You can I want 50 pascal pressure, I want 100 pascal, so you can automatically give that pressure. All the component dimension will be that back calculated in this way. So
Yes, yes.
that is the approach. It will save your time and it will save the cost as well. Otherwise, it is a endless process. Endless
Yes, yes.
process, because again you will simulate, again you will simulate, again you want. In optimization, you can get the best product dimension without. Otherwise, if you don't optimize the dimension and everything, so it's an endless process. You would do everything. You would change something. It will
Mm-hmm.
give you something in simulation, and in simulation it would take 2 or 3 days. So
Yes, yes.
somehow we need to reach to any conclusion
Yes, yes.
in the given time. That is the approach. That's why nowadays machine learning and data mining, that statics method are big company are using in their R&D part, because they
Yes,
want a optimized product within the time, because they have some time limits.
yes, yes, I understand.
Yeah, but in academic you can do endless simulation, everything you can show that one. But R&D firms are everything, they have time, and within time they have to optimize everything: space, cost, and performance. in
Yes,
in earlier slide I have discussed that you have
yes,
to
yes,
trade off somewhere, because in cost and performance, because efficiency or performance have a cost. You have to spend some cost and time to get some performance and get some efficiency. But
yes, yes,
how much you want to, how much company, how much product is worthy in that dimension, that only you can determine some statistical method or that optimization method. So that is the better tool for engineers and researcher and the people who are working in the domain of developing the product. That is better tool, that will save the time. That is my opinion.
yes, yes,
And here now we have set up of that one. And here first, well, we will go for the first, we will go units. Okay, so here for angular velocity I will give rpm, because I mostly the fan is designed based on rpm, we mostly give. And here you can different, you can define the temperature units or something unit. And in length actually I will take mm, so mm is there, mm I will take. And here pressure based model and std I will use in that one. And model you take one which first actually there are two models, viscous mostly with SST K omega and some K epsilon model. But for if the your case is purely turbulent case, purely turbulent, you know that Reynolds number is much higher, velocity is much higher. You can blindly follow that K epsilon model, any wall function or anything you can give. But if you know that your model may be somewhere in that one, turbulent and that one laminar zone, so it is better to k omega, because near the that solid surface, yeah, near the boundary layer, because first it was developed k epsilon. But in k epsilon some researchers found that it does not accurate the boundary layer effect, yeah, layer the velocity gradient near the solid surface, because some that no slip condition there would be some velocity gradient near the that solid surface. But k epsilon model doesn't capture boundary layer effect. After that k omega, it works in two way. Near the wall it will capture the boundary layer effect, it will solve that viscous sublayer, it will solve from laminar point of view. But as we go further from the that boundary layer, it will solve using the k epsilon model. So it has both the effect, so it is better because it is little bit computationally intensive. But it is better to that k omega SST model for fan. Or you are in that EV simulation, you don't know where will be, it would be laminar, where it would be that pure turbulent. So it is better, so use that viscous SST model. Here you can give that fluid domain, you can give that, in my case it is air, and I am taking aluminum for the solid. And let's go for this that solid domain. Solid domain means here is the part of fan. I gave the name fan, in which you directly give that frame rotation. Here you are rotating the frame of that one fan part. And here you can give that one, because I want to calculate in anti-clockwise direction, so -1. If you want to rotate in clockwise direction, you can give that one. And speed in rpm 1600 rpm you can give over there. And also some part of the fan, like the support and everything, that is also rotating with the fan. So you can give frame motion to that part also, so that this solid part will also rotate in that domain. And some boundary condition, that is the inlet. Here you can see some that hexahedral mesh also. If you go with that mixture one, so actually hexahedral mesh, actually it is better because it reduces the mesh count. but at curvature and everywhere you can't generate that hexahedral metal, so it's better to go with the combination. And in the inlet part, in fluent you need to give that type, and here is the part that intact fan. So it will take the boundary condition like that, and in which you show you need not to give anything, because if you give here some anything, so you are forcing the fan to do this. So automatically don't give anything. And pressure jump Pascal polynomial means there is a relation between the pressure and the flow rate, P and the Q. Okay, so basically there is a relation P and Q. Yeah, P and velocity, pressure and velocity. So basically it may be piecewise linear. If you have your, you know that your fan equation, everything. So you can give direct, or you can give that constant. But it is better polynomial, because according to the theory of polynomial, so there is equation. It will take accordingly. It will solve it. And these are the turbulence intensity, turbulent viscosity ratio that you can change according to your requirement. And another one, the outlet, nothing need to do. As the fan will rotate, it will suck the air and it will deliver. So automatically let's do the fan its work, because it will develop the pressure automatically. It will develop the suction and delivering pressure automatically. After that, wall, you need not to all, there would be no slip condition for every wall. There are, and another window, because I have give interfaces, there are 4 interfaces. So actually if you want to delete it, you want to use if you want to give automatically, first you delete. I show you. Yeah, it is taking much time. Okay, that if you want to that, you want to connect the interface. Now interface 3 and 4 are not connected. So what you would do, select 2 interfaces, 1 and 2, and auto create. The auto create automatically based on the connection, it will automatically create that interface. So now interface 1 connect 3 and 4. So automatically if you give the name interface in mesh, you can connect automatically in that mesh interface. So you not to give any contact region or anything. After that, methods, that is dynamic mesh, you don't want to reference frame. Reference frame you want to use global, because there is no local, because we have taken the coordinate origin point. And here if you take on methods, main thing, so here coupled pressure velocity coupling, you can give simple or simple C also, but fan actually generally we keep that coupled. And least square cell based matter, second order we will use. And for turbulent kinetic energy we can use second order, but now it computation cost will increase. And dissipation also, K and omega we gave that first order, so that we can easily finish that simulation. Otherwise it will take long time, because it's more accurate, but its cost of computation will be higher. And here if report definition, so here you can give that, if you want to that surface report, you want to volume flow rate, and flow rate at the inlet you can select that one. At the inlet portion you can select and give that name as a something volume, flow rate, and something you can give. So that type you can give name like that. Okay, and after that monitors you can plot in that one. Actually if you have given the name, so it will show you here, and you can plot in each iteration, and you can also get the, it will show it in your console also, what is the flow rate and what is the pressure in that one. Okay, now we will go to directly to the, actually it is showing throwing error because I gave wrong report definition. Okay. Okay, flow is already accessed. Enter unique name wants to is. Okay. After that, you need to initialize it. So better if you want to finish that in smaller time. So it is better to do hybrid initialization. And if you want to initialize from a point of view that you have certain, you are a condition and you want to compute from a specific zone, yani fan or anything, you want to set a reference point, so you can give like that also. So it depends on your whether you want. For hybrid it calculate fast, so mostly hybrid you can do, otherwise you can use. After that you can save which how many iteration you want to save, and run calculation means you can save give the number of iteration what you want, and then the next time you can calculate. Okay, so that is about to fan. Time is lesser. Okay, so we will go to that one, EV motor part, because it will also take some time. So we will quickly finish that. Will take some time to go down till time we discuss that motor part. Yeah, my screen is visible to you.
Yes, Akshay, it is visible.
Okay, so that is E motor in which that fan is installed. That fan is installed, and first that outer part is the outer fluid. Outer fluid. Let's first that one. Okay, now this is
Can you give idea that where you have opened this motor part?
that is space claim.
Okay, especially.
Yeah, yeah.
And you
In
have
space claim,
already created this motor part.
actually in space claim it is easy, and it is now it is easy and faster way to calculate to design the product. It is in design modeler you can develop, but it will take more time. So nowadays company
Yes,
has been shifted some space
yes,
claim and some better designing software. So in that it was developed in that space claim, and that is the motor casing. I show you different part. First one by one we see. First, we will start from where? We will start from the shaft. That is the shaft of the that motor, and after that we will start from that one rotor. That is the rotor part, and in rotor you can say shaft is connecting to the rotor, and here you can say some gaps are there. You can say that some races are there. So magnet will be placed in that magnet. One magnet. So these are magnet that would be placed in that one recesses, and after that there would be a outer T cover, casing, fan cover, and raptor के बाद we will go for stator part, stator or coil part here. And where is the stator? That is the stator. Okay, so here you can see, you see that assembly shaft and rotor. In rotor magnets are there, the rotor will rotate, so it will rotate the shaft, and that are the end winding, electrical winding, that one. And that is the stator part, it will be fixed. Okay, so based on electromagnetic effect there is a that magnet, and because of that one copper winding there is EMF generation that would rotate the shaft continuously. After that we come in the bearing, that is D bearing. D means that is bearing. D means drive and bring, and non-DE means ND with non-driving end. Driving end means that side will couple to some, you can say, some driving component. Driving unit means it may be car driving unit, it may be rickshaw, it may be bike driving unit. Okay, after that, here one thing or I also want to see, that is filler. Okay, so here you see, if you minimize the filler, so that is a gap. Okay, so basically what happens, that winding doesn't contact directly to any part of the stator, otherwise electric current leakage will occur, and all casing, all part will have some electricity. So to prevent that electric loss and everything, so there is a thin layer of the filler, and that is electrical insulating material between that stator part and that one. And the main purpose of this one, to remove any to prevent any current losses to the stator or any body of the motor. That's why it is provided. After that, that is cover, that is drive end cover. After that, it will connect to the driving unit, and after that we will go to ND bearing, we see, and ND cover also, that is ND non-driving end cover also. And that is the casing. Casing means here are the fins that will use to that remove the heat. And after that, there will be a fan. You can check that fan over there to flow the air from that. After that, fan cover will come, then you will get idea how it is sucking or how it is giving. You see, there is a hole, air will go through this hole, and you can see that gap over there between the casing and the fan cover. And you will find that fan will deliver the air to that casing part. Okay, so that it can cool the casing. And actually it is conjugate heat transfer, it is a small motor, so it's a air cooled, so in which heat is conducted, because all the parts are interconnected, heat is conducted from the that magnet, from the rotor, and from the end winding, and it is convecting to the ambient air and the air that fan is providing. So it is a conjugate type of heat transfer process. And in that, because we want outer fluid, because after casing we have to generate a air domain or enclosure also, so that we can provide a fluid domain outer the casing. So we have developed a fluid domain or air domain like that. Okay. Okay, and we have created inside that one volume is the inside that fan cover. We have also created fan domain, and we have connected that outer fluid and that inner fluid. Yani the fan domain inside that one fan cover, so that it will be connected, and so that flow can occur. If you don't connect that outer fluid and that fan that is coming, air that is coming from the fan, so it would not have a connection. So you should maintain the continuity of the flow in that one space clamp. And that in that one, if you in space clamp, that is a good tool. You can also that you can check whether there is any extra edges to found some area, and you can fix that area. It will automatically fix that area. Okay, now there would be there are no extra joints to remove. And also, if you want to repair here, actually in space clamp, if you want to learn, it will take time, because but it is, if you once you learn, so it will automatically update the geometry. If there are some inexact edges or something, no area is found, or there are some interference also, there is some intersection between different parts. So you can, because in that complex body there is a chance of some intersecting bodies. So here in that one you can check also intersection. Yeah. One another thing, missing gap stitch, and that one merge face inexact we have checked. And we prepare means interference is there, so it will check if there are some part intersecting each other. Otherwise mesh would not be generate if you don't remove any interference and intersection of the bodies. So that is a basic, only for basic use purpose. You if you want to, if you don't have any expertise in space climb, so it will take time, but your works will be easy, so no area will be found. Okay, so here after that we will discuss the meshing. Okay, it is closed. Now we will open a different fluent. So for complex bodies, it is better to use that fluent meshing, because it developed that that we will for higher body, for big bodies, it is better to develop that polyhedral meshes for that one, because it will reduce the mesh count if we take any body. Yeah, first meshing. Yeah, it will, I will show you the mesh how can we develop in fluent directly, because in workbench meshing it takes lot of time, and it also increase the number of mesh count. But in fluent it develop the polyhedral, so it is easy to generate, but you need, your geometry should be properly clean, and there should be no you can say extra edges, no interference, and no another thing. Otherwise it will stuck somewhere in meshing. But if you think that your geometry is clean, properly clean, so you can go directly that fluent meshing. It is easy. It will take some time to load.
So while it is loading, if any audience has any question, you can.
You can ask, because we are running short in time. It
Yeah,
is
so you
already
can
one.
raise your hand and we can ask the question if you have any question. Amit, your voice is not clear.
Yeah, hi Akshay. I am Amit Raj, postdoc in at IIT Bombay. So I
Okay,
have
okay.
some query. Means you have shown your means the modeling of the fan and the
Hmm.
modeling of the heat transfer in the motor.
Yeah,
So
yeah.
can't we? You have done this in means uh, Fluent or in Open Form or in ANSYS. So can't we do this in Abacus? Because I am very means familiar with Abacus. So
Okay,
yeah, means for the motor part, there is also one electromagnetic model available in the abacus.
okay.
So
But that electro actually, I don't have much experience about the abacus, but mostly people use it for that structural on any type of analysis. But
okay,
but I am not very expertise in this abacus. Tools may be different actually, but it's only concept how we design, how to calculate, how to tools may be different, but the physics would be same. So basically, if you want to use abacus, so you have to explore that abacus directly. Okay, how can we generate any fan in abacus? You can also, obviously you can generate any fan or any body, but I don't know much about that heat transfer and anything in abacus, because mostly people I have seen that they use it for structural and
yeah,
that
yeah,
type of
exactly.
FEM analysis or anything.
Uh, uh,
But if you have an idea that if it can be used for that heat transfer and flow analysis, so you can tell us, we can also get. Have you ever used for fluid flow and heat transfer?
no, no, no. Actually, not exactly fluid flow, but I have used some SPH means a smooth and particle hydrodynamic. It is also like a means for a severe deformation. Actually, I have model means fixer ester means additive fixer ester deposition. That
Okay, okay,
deposition part means it is just like a fluid flow or that material flow just behave like a fluid flow. So that
okay,
thing I am modeling using SPH model means where that our FEM element changes to the particle
okay, 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 okay.
so that it can yeah means capture our that flow process and various post processing can be done there through the particle only.
Okay, then it can, but it require, it give the that continuous flow and heat transfer modules are there,
No,
like
no,
if you
yeah, actually, still I am working on that. Means I'm not. I haven't reached at that level, so
okay,
that
okay,
I can extract those data. Basically, I am predicting the loads for that.
okay, okay,
Uh,
okay, okay. Actually, I
So
don't have much idea about that.
yeah.
I think that SPS that you are discussing, that is kind of a messless method. There is no
Ah, yeah,
mess.
yeah, mesh free method. Just that is element it changes to the particle. Yeah.
Yeah, so I think that is completely different from what Akshay is doing.
Okay. Yeah. Yeah.
Okay, okay, bro. We will discuss after that.
Sure.
Okay.
Sure.
So
Sure. Sure.
first, actually, we see that meshing. Actually, first I show you how can we develop. First, import the geometry. After that, add local sizing. Means if there are some option, and if you want to generate any local sizing somewhere, so it you can, yes, and in that automatically that body will come, and you can give local sizing if you want for that body. And in that one, yeah, it will taking time, otherwise I will.
Akshay, there is one question in chat box.
Yeah, yeah. Could we take question answer session after that, because I will take only 10 minutes because we
Yeah,
are running
actually,
here.
you are means while you are running the system, then we can reply this question. That's not a problem.
Yeah, is there any boundary related to heat generating, binding, and rotor? Yeah, Nitish, I will show you in that next setup. I will show you how can we define the boundary condition related to heat generation in that one, because now that motor part is remaining from that heat transfer and fluid flow point of view. So I will show you. Wait some time. So here, as we were discussing about that one, face size, that one local sizing, so we can give local sizing directly to anybody. Different parts are coming, so we can give local sizing anywhere. And here create surface meshing. Here we can give surface meshing anywhere, and we want to scope proximity faces near to faces and edges also. And there are some gaps between the body, so we will put two cells per gap. And we also that one maximum minimum size it depends on the what is the minimum, you can say, gap size or minimum size of the part in your body, a part or the age you want to capture. So you can give that minimum size, and maximum sizes upon the accuracy you can give 4 or 4.5 something. And in that you can create the surface meshing. And in describing the geometry in geometry type, because our geometry consists both air domain and fluid domain. So here you can get geometry consist of both fluid and solid regions. And will you extract fluid region? No, because we already gave. If you want to here extract the fluid region from somewhere, so you can directly select. But we have already in design space claim, we already given that fluid domain, so we need not to give here. And change the fluid down from wall to internal. Very carefully need to consider it, because there are some because air in fluid domain and fan inside the fan what is different, and fluid domain in that outer way is different. So they need to connect somewhere. So if you see that change the all fluid from wall to internal, automatically it will create a wall between two fluid. So you need to change in wall to the internal, so that you can get a continuity of the flow. And need to apply shear topology. Shear topology is that option in space claim where it shear the edges faces from body to body, so that heat transfer, conduction, convection can occur. So we actually mostly here we can also do, but mostly we do in that one space claim. There is option shear topology. Here also we can do the shear topology to connect the edges and the face, and update that boundaries. Here it is not coming. Okay. I have to open it again for that. Okay. Fluent. First, I show you that model. How can we give the boundary condition? We directly go to solution. We will case and that one. Okay, we directly go to the model. Here I will show you how can we give the boundary condition to the that EV motor simulation. Yeah, that is. Yes, yes. Yes. Okay. You can see the mesh over there. Here also, if you want to see, there are actually it is not showing well. So we will see in that one mesh. Where is that one? Yeah. Okay. They are mostly that are polyhedral mesh. Okay. Whether the benefit of developing the polyhedral mesh means it has large connected and it has a large number of connected ended so that it can cover more area in that one smaller mesh count. So mostly in if you have that big setup or that big assembly. So it is better, it is if it is possible, because polyhedral requires very you can say accurately that body cleaning and geometry cleaning, but it gives faster results and it has reasonable accuracy. And if you're with tetrahedral and with that combination of the tetrahedral and hexahedral, if you have less mass counted 6 crore and 8 crore, so in that one polyhedra it would be around 1 crore, 18, 1 crore or 1 crore something. So it is better. And here I show you how can we model the set. The first way energy would be on, and viscous ST here we will use. Here it is it is the entire setup. The fan will flow the air and it will throw it in the casing. So it would be, and energy means the heat transfer in that one, that winding or thing that we will give. And liquid material, here is only the fluid. And if we talk about solid, ADC 12 for the casing of the that motor. Aluminium also some part will be the motor. Copper is the winding of that motor, winding material. En24 is the that shaft material. Magnet material we have taken for that magnet in rotor. And PP is the polypropyl, that is the fan material. Mostly in that one, some fan are developing using some that combined material to actually to minimize the that cost as well as the material required. And rotor stator material is different. SS have some that bearing have SS material, and Warnis has the that insulating material between the that stator and the winding. And one is the cell zone condition. If we talk about that, is the fan domain. And you check in the fan domain, we give that boundary condition. Here we have to give that frame motion in fluid domain, and we have to give -1 anti-clockwise is there. And if we want to that speed RPM 1600. Okay, after that solid, that if we talk about coil here in cell joule condition. So if somebody was asking that how when ki give that first that it is coil, so we have already assigned the material. So here we can select that material, and in source stuff you have to click on source term. And one source term mostly we give in watt per meter cube, mostly. So here we can depend on the body sizes of that one winding. Actually, so we can give that watt per meter cube in the source term. Basically here one is the source term. Every coil, because different coil we can copy from one coil to another also directly. And in also filler also we give the material that varnish. Okay, and that magnet also generates some heat. So in that magnet also we give that source term, that is watt per meter cube, that is heat generating from that one. Okay, same some heat will be frictionally, they will rotor, and that one stator and rotor will also give. So we can also give to that in the volumetric source sum. In that one we can define right away. And in the boundary condition, because there is a inlet and here is the outlet here. So in inlet we have the fan or inlet, so we will give the intake fan condition over there. And outlet we will give that outlet pressure outlet only, because it is ambient. Okay, so here report definition, we want to check the temperature of the winding. We can select here, we can select the volume average temperature, means because that heat generation rate is volumetric, means source term is volumetric, means that coil is generating some watt per meter cube. So here that we need to calculate the volumetric temperature of the coil, so that we can get the idea of that temp how it is rising with each iteration. And flow we can give inlet, we can measure the flow, how much flow that fan is giving. And monitor we can plot in that one. And same way initialization hybrid we were doing. And here we can calculate that one, but it will take one day or some hours to calculate properly, because that is complex geometry. So that it will take time, but there is a way how can we uh, that set up any case in that way. And one thing also, because here we have done that share every age and faces, so automatically it will conduct the heat, and through convection, because air is flowing over there, and we can give actually in that one, once once need to check when we are giving inlet, so we need to assign the temperature also. Here is the bullet point thermal. So we are taking ambient temperature of 58 from safety point of view, because nowadays the ambient temperature in that, actually in that one I have discussed that we have to design the thermal management system for every operating condition. Mean in some that in terms of winter temperature maybe 20 or something, but in that summer zone in some north areas like Delhi and somewhere else, temperature may go up to 50 and 52. This time it went to 52 or 53. So it may go in some times, I think global warming or something, it may go around 55 or 56. So you need to design in such a way that if that machine is running in any ambient and operating condition, so it can sustain. So you have to ready, you have to design for the worst condition, what might be the maximum ambient temperature. So that we need to consider. So that's why one of the that challenge is one thing, we need to design one setup for every operating condition for higher, because big company they don't design. If let's see a car making company design a car, means it's a global company, so it will design everything for entire global level. It will not design separately for different region, like for this country this much, for this country this much. So actually we need to design such a way that it can work in every operating and worst condition. Yeah, that is for it is around 155 151, Pratyush.
Yes, yes. So there
Yeah,
is one
we
question.
now they can ask any question.
So like there is one question, boundary condition.
Yeah, that is the boundary condition. He was asking about that. How can we define that heat generation? Heat generation is a zone condition. We can define its source term, and basically in source term we can give. Actually, in that one, if we are doing in motor, so we can divide that volumetric heat generation source term. But if we talk about that electronic, sometimes we have to give the flux in that heat per surface area, heat generation per surface area. For electronics, that is different to depend on the that what is the that application, we can define the heat generation rate, whether it is volumetric surface or something, or whether it is a localized heat generation rate. Maybe heat is generating from a some point, means some direct heat generation. We can say we talk about MOSFET and some chips and something, so they generate the heat based on surface, because they have very lesser volume as compared to the surface area.
Yes, yes. Anyone have any other question? Please,
Any further question?
you can raise your hand and you can ask the questions. Yeah. So there is question. How can we use a radial fan in ANSYS ice pack, as there is no option for the radial fans in the ice pack? Akshay, can you see the question?
Yeah, once Sila actually, yeah, was
Can you
first
see the
was
question, Akshay?
how can we use radial fin as there is no option for radial fan in aspect. Actually, if you want to generate a radial fan, Imtiaz side is asking that how can we use a radial fan in the ANSYS aspect if there is no option for radial fan. You can also import from design modeler or that one space clamp. You can develop a radial fan, because in icepack I am telling you, icepack in that you can't design a fan. You can put a fan and it you can directly that fan is developing that volume flow rate. But for designing purpose you can consider that this is blade generation for that one, and you can import it to the ice pack or somewhere else whether you want. So it is better if you want to use any that one specialized fan for any application.
Yes. Sir, there is another question. Like, is there any limitation of the fin length in heat sink design?
Is there any limitation of the fin length in heat
Actually,
sinks?
yeah, you are
Uh,
explaining something. Then you can finish that. Then after that, you can answer this question.
yeah. Actually, if you see the overview, how can somebody can get the expertise? How can somebody can get ready for that EV thermal management job? So here you can see that there are step by step. First, you need to know. First or mandatory, people use that GUI based software like a black box. They give something or they get something, so it is different. First you, because it's a machine, whether you provide something it will give you some result. So for and basic understanding, you need to know about that analytical formulation and conceptual modeling of any system, whether it's sink, design, fan, and everything. So first you should learn about that analytical and theory of fluid flow and heat transfer, and how the turbulent flow and every model can work, and how can we use it for our particular application. Then you should know, and you can go through some courses and some books for reading it. And after that, after developing that, you design your a basic system, simulate meshing and something. And for that you should fan design, which is called heat sink, electronics, cooling. And after that you can develop, there is one thing also, heat exchanger also, and the theory of spray cooling, immersive cooling, that you need to know for further simulating in this domain. And after that, if you have, now you have two things, analytical modeling and CFD modeling. You would have some points of data, some data points that would you get from analytic and CFD. After that you can apply that prediction model for optimization, and for that one, that for if there is such a temperature somewhere, so how much flow rate we need to flow over that body to cool up to a some temperature or up to a optimum temperature. And based on that prediction model, you would have much data, so you can optimize your cost and performance, that I have discussed in the previous slide. And you can make a decision, okay, which one it would be better. And so from this point of view, that for a you can say for a complete package, for a complete or for becoming a engineer who can develop a product entirely from rough design or from basic point to a complete product, so you need to know everything. It's a step by step procedure. You either you learn some software, it doesn't mean that you can develop the software, you can develop the product. So it's a step by step product, so you need to know about everything.
Yes, yes.
And yeah, if you want to become a CFD analyst only, CFD analyst who can, you somebody provides some geometry and model, and you need to run it and provide the result. That is another job, that is CFD analyst job, that is different. But for that also you need to know different model, how can we model spray cooling, how can we model phase change, how can we model that one. So that is also CFD analysis. But for a product manager, a product engineer, so you need to follow these all steps. And actually if you see the flow chart, simulate, if you develop a first rough design, after that simulate it, and if it getting the desired level, you will go through the part. If it you are not getting the desired level of product, so again you will go simulation, again you will change the dimension or something. So that is the complete process. Anybody want to work in this domain, so he has to know everything about it. Then he can develop any product from basic to that
So yes,
advanced level.
there is next question that I say will get. Is there any limitation of the fin length in the heat sink design?
Okay. It's depend on the actually length. If you ask me thickness, so I would have some actually idea, because you need to keep the fin thinner and thinner, so that in the you can get maximum surface area in the relatively lesser volume or lesser material. But fill length, it depend on the how much space is available for the cooling, because you want to generate, it depend on, it varies from application to application. If you think about that 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 electrical motor fin, it has different fin length or something. And if you think about that one, some you can think about heat exchanger, that would have some different length and thickness, will vary. So it depends on the application. And basically if you increase the fin length, obviously up to certain level heat transfer rate will increase, but after a certain level it will not increase, because it will reach to the equilibrium. So it's depend on the how much flow rate, what is the temperature condition, up to what length it will come in the equilibrium with the that flow system with the flow. So it's a dynamic question. You can't say that this much ke 5 mm is 5 mm it would be the fill length. So it's, this question is different, it can't be like that way. It totally application based. But if you want to that one optimize that fill length, so basically what you do, you take a rough fill length based on your calculation. After that you see, you do the simulation and check up to what length of the fin system get the equilibrium with the fluid flow. If it get the equilibrium, that there would not be any heat transfer, because both the temperature would be same, there would be no temperature difference. So it is a simulation part. First you develop your that rough design, after that simulate and see, visualize that up to what, and you can optimize that one, what fillet should I take.
Yes, so length of heat sinks should be optimized based on the thermal efficiency, mechanical, like Akshay said, that space constraint is also important, and also the cost
Yes, yes.
effectiveness. Yes, so any other question? So Akshay, I have one last question apart from
Hmm.
whatever you covered. So you have
Hmm.
discussed that. Okay, there is one other question. No, Subhajit, there is Akshay said that there are many factors like space constraint is there, thermal efficiency is also there, and cost effectiveness is also there.
Yeah, thermal equilibrium is also there.
Yeah, yeah.
Yeah. Hmm.
So there are many various factors is there, and that is depend upon your application, that what purpose you want to do. On based on that, it's like if you are using for a specific purpose, there is a space. Within that space, you have to design the thermal cooling. So it depends upon applications that what should be the length of that. I'm right, Akshay, I think.
Yeah, yeah, you're right.
Yes. So Akshay, I have question that like you have discussed about the cooling system, there is various cooling system.
Hmm.
So
Yes.
there is another one system that you discuss about the solid state cooling system.
Solid state cooling system
Yeah, yeah.
is solid state cooling system means we provide any that highly conductive material, solid form means actually want to conduct the heat from a that heat source somewhere to other part. You want to see that from that one rot casing stator of the motor, you want to conduct the heat to the that one motor casing, because heat is mostly dissipating from the casing
Yes.
using the air or something, yeah, any fluid. So basically what would do if you put any that highly conductive material between the stator and the that casing, so it will conduct the heat from that winding zone to the that casing efficiently. Or you can, it is mostly that material base. If you have any idea that you can put a highly conductive material between two interfaces, so it will increase the heat transfer rate, or it will increase the conductive heat transfer. Or otherwise it's a gap or somewhere else, yeah, you have something that is you can say lower thermal conductive material between, so it would reduce the heat transfer rate, yeah, heat dissipation rate from the body. The
So
solid state means
actually, I saw one means solid state cooling device where
hmm,
there is a they used ultrasonic waves.
Okay, okay, yeah, some,
That
yeah, yeah.
that
There is,
sucks the air,
yeah, 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 yeah,
sucking the
yeah.
air. They
Yeah, yeah, yeah. That is one aspect also. We can use that Peltier effect also. That one, in that one, you can cool any body using some, that one ultrasonic and something. There are some, but these are costly. But if you want to cool rapidly to any system, so that is use that. Yeah, you are right. Actually, solid state cooling in that aspect also can be used. That.
So actually, I
Um,
wanted to ask that that kind of the cooling devices, solid state cooling devices, where it is ultrasonic waves are used, that is also being utilized in the electric vehicles. Or
in elect no, no, up to that level actually they can't be utilized in electrical vehicle, that Peltier effect and something, because it is costly, and also there are some limitation to use these, that Peltier and everything, and they require some EMF or something. So they still now company, any industry doesn't use that EV type of industry, but they have any other application in other area like defense and some space application, that solid state devices.
but
But in
what if it
battery
is,
cooling, but you are right, in battery cooling I think people are using that
I
solid state.
particularly see the application like electronics coolings for that solid state.
Electronics cooling I don't have much idea, but some people are coming with that, because nowadays battery cooling is a the crucial task, and actually people are developing that fast charging batteries, so that for rapid cooling of the battery during the fast charging, so they are using that type of devices that developed on Peltier effect, that is called solid state, that one.
Yes, yes. The another question is there for medium power applications like a rickshaw, which cooling is better, motor or battery? Sorry, which is cooling better is for motor and battery?
For e-rickshaw, I think it's air cooling, because e-rickshaw, you see now that e-rickshaw battery power rating is around 1 kilowatt to 1.5 kilowatt. Okay. So
Yes.
in that one, if you develop any setup, means any external cooling, as a liquid cooling, anything, so they will actually consume more power because it has a lower power rating. And actually by air cooling system, actually in that lower power rating, like if you talk about that one e-bikes and e-scooters, or you think about Ola and everything, they use that natural convection and air for cooling purpose. But that bike and scooter, they don't use that one fan. But in e-rickshaw they have shaft mounted fan. They don't install any external fans. External fans means which have that external power supply that would come from battery and other thing for another electrical medium. So what they do, they use a shaft installing fan, in which the fan is installing on the that e-rickshaw motor shaft. So it will, with the as e-rickshaw will moving, so that fan will also moving, so it will suck the air and it will throw it on the casing of the meter. But no external agent is required, otherwise the efficiency will decrease, because it's a lower power rating application.
Yes, yes, and also low
Yeah,
cost
low cost and lower power, because I think motor prices is very low. It would be around 6,000 or something. So we can't use, or there is no requirement. But mostly liquid cooling got famous from two three, got from two three applications area. First one is the that high power rating cars, means that SUVs, yeah, Audi cars, and that one Tesla high power rating car, which requires 180 kilowatt or 150 kilowatt power rating motor. And another one is that data center nowadays company, because nowadays companies are developing more data center in every country. So more data center cooling is also a crucial task, in which they are using that liquid cooling. Otherwise their component will fail, they will not survive for the longer time. Because if you install any data center, so it will capture a lot of capital cost, because it will take lot of area and something, there would be lot of component. So for that actually they need to do some actually long time safety issue they need to ensure, so that they are going for immersion cooling, spray cooling, and some heat pipe also, and some PCM. But now they are shifting to that hybrid type of cooling, They are using everything to make the system better.
Yes. Yes. Yes.
Yeah.
X-ray cooling is not effective for the some of the reason the cost.
No, 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 no. That will not. Cost also or power rating also.
Yes. Yes.
Because if you see spray cooling, they need a external pump to spray the air and actually nozzle also. So how can we arrange that nozzle and
Yes.
pump? It,
Yes.
it will require more power. So there is no application in that.
So I think there is already we have means ahead of the time. So and we have no any questions.
Okay.
So I would like to means final comments from you, and then we can end this session.
Okay. Thank you. Thank you everyone for joining this session. And actually we have discussed everything, but actually in that webinar we can't cover every topic because here for different cooling and different components, actually we require one class each. For actually optimization and machine learning, we require 5 to 10 classes. But we have covered that outline of the that one. How can we proceed in that way? Hopefully you have enjoyed that webinar, and hopefully you got any basic understanding of that one, ev thermal management. And thank you for joining it and listen me for entire session for 2 hours. I think it went around 2 hour 10 minutes.
Yes, more
Yeah.
than 2.5 hours.
More than 2.5 hours.
Yes.
Yeah. Thank you, Pratyush, for supporting.
So thank you, means thank you Akshay for accepting this means on a single call you accepted this invitation for this webinar, and thank you to all the audience for attending this session. And we are again going to organize a few means other webinar on the abacus also, and there is going to be one webinar on the uh, dynamic mesh movement also in upcoming 2 or 3 weeks. And we are going to also organize means you can just suggest some of the ideas. I have already shared my email of iterasim@gmail.com. So if you have any queries or any feedback, you can share your feedback and query. And if you want to conduct any other webinar, you can just mail me the details and summary of that what you want to means conduct in this webinar session. We will means try to do our best. Okay. So with this, I would like to thank you all of you and thank you Akshay. And maybe with the support of Akshay and other teams, we will come up with one full developed course on this electrical vehicles, starting from the ANSYS basics to the developing means simulating